Okay, let us see how to find norm of a vector. Norm of a vector, like in quantum, is same like the one which we do for real numbers as well. Of course, in quantum, we are in complex plane. So norm of vector is nothing but the length of the vector only. Of course, a qubit is also another version of a qubit, or ket is nothing but a vector only, another name also. But usually we go with ket version. Okay, it's nothing but norm of ket xi. Norm of ket xi, how do I define it? It is under root of inner product of ket xi. What's inner product? You can check the other videos, previous videos of mine for inner product in case you have it out. Otherwise, it is just the product of ket xi and its dual is nothing but inner product. Under root of inner product is nothing but norm. Okay. Now, how do I normalize a vector? Normalize a vector, as in vector spaces we have seen in real line. Here also, how do I normalize a vector or a ket is ket xi divided by its norm. Would be the normalized vector, normalized vector of ket xi. There are no two lines. Ket xi is just one line and one greater than symbol. Okay. Yeah. Let's see one question. Let's see one example so that you understand the concept of normalization. Of course, it's very simple, provided you have a proper definition of it. Okay. Example. Check if ket xi given by 1 by root 5 ket phi 1. No, just a second. Ket u1 minus I 1 by 15. Of course, I by 15, whatever. I by 15, I can just write. I by 15 ket u2 plus 1 by root 3 ket u3. Check if ket xi can be normalized, can be normalized what is given is given ket u1, ket u2, ket u3. Form orthonormal basis. Form orthonormal basis. Okay. Also find the probabilities is an extra question. Also find probability of each state. Find probability of each state. Okay. Let's see the solution for it. And then all the other things are obvious. How do I normalize it? If I have ket xi, I have to find dual. It's a dual of ket xi. It would be called bra xi, denoted by this symbol, and it is nothing but the conjugate. Dual of ket xi would be bra xi, which is nothing but conjugate. Okay. So how do I find the conjugate? Please see here. Carefully write the notation and then things are done. Okay. Instead of ket u1, I'll be writing bra u1 minus Instead of minus I, conjugate of minus I would be plus I by 15 dual of u2 plus conjugate of a real number is itself. So no change. Dual of u3 is what I will write. And once I have the dual, I'll go with the inner product. Okay. Inner product of Kets I is nothing but the product of Kets I, dual of Kets I into Kets I. Okay. So I have both of them. 1 by root 2 into 1 by root 2 is 1 by root 5 into root 5 is root 5. I will be having something like this. Not u2, it is u1. I into I is I squared. So plus I will be having 1 by 15 u2, inner product of u2, plus 1 by 3 inner product of u3. You can ask me, what about the other combination terms, u1, u2, u2, u3 kind of things. See, there's this condition that u1, u2, u3 form orthonormal basis. What is orthonormal basis? Let us see. Orthonormal basis. They form orthonormal basis. That means what? Inner product of u1 with u1, u2 with u2, and u3 with u3 would be 1, and inner product of u1 with u2, u2 with u3, and u3 with u1 would be what? 0. That's when I can say they form orthonormal basis. Okay. Hence, inner product of Kets I would be nothing but 1 by 5 plus 1 by 15 plus 1 by 3. I'll just take the LCM and finish off the calculation part. Okay. So what I'll have will be 5 3s 15, 15 1s 3 5s by 15. So 9 by 15 is what I will have. Okay. Instead, just see here, I'll make one small modification. That is, if I had, of course, it is root 15 is what I think I have taken. Just see here in the question. If I had I by I into root 7 by 15, I into root 7 by 15. Okay. Then what would have happened is I would have got here 7 by 15. Okay. 15 into 15. 25 is what I was supposed to be writing. Okay. And then this is 7. Okay. This is 7 again. 8 plus 7. Is 15, which is 1. Norm is 1. If norm is 1, then I can normalize, or something like your unit vector. If norm is 1, I can say that that vector can be normalized or something like that. Okay. Yeah. What I will say is, hence, Kets I is normalized. Normalized. Suppose if I'm asked to find the normal vectors, okay, then what I will do, the normal vector of the given vector, then I will just divide the vector by its norm. Okay. Now we have also been asked to find the probabilities. The question is probability of each state he has asked. Okay. So what are the states that I have? Probabilities of Ket U1, Ket U2, and Ket U3. They have asked me. Now, probability definition is nothing but, just see here, coefficients. Suppose if I have, I'll go probably in the next video, I will again go with the proper definition for an n-dimensional space, how we calculate probabilities. If at all, if I'm being asked probabilities, then it is alpha into ket u1 plus beta into ket u2 plus gamma into ket u3 if I have, then probability of ket u1 would be nothing but mod alpha squared. What is mod alpha squared? Alpha into its conjugate. Alpha into its conjugate. Ket u2 is nothing but mod beta squared, which is beta into beta conjugate. Okay. U3. Ket u3 is nothing but gamma into its conjugate. Okay. So alpha is what? Alpha is 1 by root 5. So 1 by root 5 whole squared it is. It is nothing but 1 by 5. Okay. Next, beta is nothing but, beta I have it to be I root 7 by 15. I have modified na. Minus I have a plus I have in the ket. I have minus. So its conjugate would be plus root 7 by 15 I will have. So it is nothing but 7 by 15. And then this would be what? 1 by root 3. 1 by root 3 whole squared. It's a real number. So 1 by 3 it is. And again, I can clearly see the sum of all the probabilities of all the kets. Sum of probabilities of all the kets turns out to be 1. That's how I will calculate probabilities. Of course, in the next video, I will go with proper definition of probabilities and density functions. Okay. Yeah. The next important topic that we have in quantum is, I have seen partially something related to superposition. The next important topic that we have in quantum is tensor product. Once you know how to find tensor product, then some of the things will turn out to be easy. Of course, I will just finish off one problem on how do I normalize any vector. Okay, find the normalized state. Okay, I'll just finish off one more example. Find normalized state of normalized state or normalized vector. I can say normalized vector of Kets I. How is Kets I defined? Just see 3 ket 0 minus 2I ket 1. Okay. Of course, norm is nothing but the inner product. So what I'll do, I'll consider the inner product first. Inner product is nothing but, okay. So what would be the dual of Kets I? Dual of Kets I is nothing but, I can, of course, guys, there are two versions here. Let me do both the versions. Okay. 3 into 1 0 minus 2I into 0 1. Ket 0 is 1 0, right? 3 0 and ket 1 is 0 1. So minus 2I, of course, I'm sorry, this is 0 and 2I. Okay, this is one version of writing the matrix. And then, of course, it's a dual. Its dual is nothing but Kets I cross, that is conjugate transpose. Okay. What would be conjugate transposes? 3 minus 2I conjugate would be 2I. And its transpose would be a row vector. 3 and 2I. Okay. Right. The other version of dual. Just see here. This is nothing but 3 instead of ket 0, it's dual na. So bra 0 plus 2I dual of ket 1. Okay. Yeah. This also will result in the same thing. You can just see here 3, 0, 1. No, this is 1, 0, ket 0, na? Yeah, plus 2i, 0, 1. Okay, so this results in 3, 0, the row vector, and 0, 2i, the row vector. So it would be nothing but 3, 2i, because we'll add the respective components. Okay, yeah. Now coming to the inner product, this is nothing but 3, 2i, 3 minus 2i. Okay, so it would be nothing but 9, 3, 3 is 9, 2, 2 is 4. Of course, with a minus sign, I into I is I squared. Again, it's with the minus sign. So minus and minus goes to plus. So inner product, it would be nothing but 3 and 4. Okay, now if I find the norm, just a second. This would give me a single element. 1 second. Yeah. A row vector into a column vector would be nothing but 3, 3 is 9 plus 4. This is nothing but 13. Okay. Norm is what? Norm is equal to under root of inner product. Under root of 13 is what I will get. So how do I normalize a vector? Normalize the vector Kets I. Normalized state or normalized vector is nothing but Kets I by its norm. Okay, it's nothing but Kets I by norm of Kets I. Okay, so Kets I is what? That I've got it to be 3 to I. Okay, so by its norm is nothing but 1 by root 13. So it is nothing but 3 by root 13, 2i by root 13. This is the normalized vector of Kets I. Okay, this is how I'll find out. Okay, coming to the next important topic of quantum, that is tensor products. Tensor product, how do I find? Of course, tensor product between Kets is very easy. Tensor product between operators is a bit a different thing, which has to be taken into proper account. Okay, so let me define first tensor product. How do I find tensor product? Okay. Suppose if I have two Hilbert spaces, let H1 and H2 be two Hilbert spaces of dimension n1 and n2. So tensor products helps us to construct a Hilbert space of dimension n1 into n2. Okay, yeah. We can construct larger Hilbert space, capital H, which is denoted by capital H is equal to H1 tensor product H2 of dimension n1 into n2. Okay, yeah. Just see here. Let ket phi 1 belong to H1 and ket phi 2 belongs to H2. Then ket xi, which is equal to ket phi 1 inner tensor product ket phi 2 Kets I is called the tensor product, is called the, let's see how we'll do it. It's very easy. Called the tensor product. Okay, fine. Yes, let's see an example to understand things better. Okay. Yeah. Example, if ket A is equal to 1 by root 2, 1 minus 1 and ket B is equal to 1 by root 3, root 2, 1. Find ket A, tensor product ket B is the question. Okay. So see the solution, how I'll do it. Ket A, inner product ket B is nothing but ket AB. Shorthand notation of tensor product is ket AB, guys. This would be nothing but 1 by root 2 into 1 by root 3. I write it outside because both are constants. Of course, properties of tensor products I'll talk about once you understand. Okay. Yeah, right. 1 into root 2, 1. Okay. And then minus 1 into root 2, 1. Okay. So what do I get? Just see here. 1 by root 2 into 1 by root 3 is 1 by root 6, guys. Okay. Root 1 into root 2, root 2. 1 into 1, 1. Minus 1 into root 2, minus root 2. Minus 1 into 1, minus 1. So this would be the resultant tensor product. Of course, to make things more easy, we can check with ket 0 and ket 1 also, guys. Okay. Ket 0, tensor product, ket 1. See, because these are trivial things, I think you can understand it much better. Tensor product is denoted by cross and enclosed with a circle. 1, 0, 1. Okay. 0, 0, 1. Okay. So 1 into anything is itself. So it is 0, 1. 0 and into anything is 0. So I'll be getting this. Of course, the shorthand notation for this is 0, 1, guys. This gives rise to, tensor product gives rise to multi-qubit systems. Okay. Till now, I was in single qubits. Now, tensor product shorthand notation gives rise to multi-qubit system. Okay. How do I do the same thing with matrices? Let us see. Tensor product of matrices. How do I do? Let's see. Okay. Suppose if I have A is equal to A, B, C, D. Okay. Capital B is equal to E, F, G, H. So how do I find tensor product of A and B? Okay. Just see here. A, E, F, G, H. B, E, F, G, H. C, I'm sorry, this is not G, it is C, E, F, G, H. D, E, F, G, H. Okay. So what do I get finally? It's going to be very huge, but then it's fine. Okay. This will result in a 4 by 4. This will result in one more. No. What's it? 2 by 2 only, no? No, not 4 by 4. 2 by 2. Okay. And this will result in 2 by 2. 2 by 2. 2 by 2. Okay. You can imagine what can be the magnitude or how much dimension the matrix is going to be like. Okay. 2 rows, of course, again 2 rows. This is 4. Okay. And then 2 columns and 2 more columns. So 4 by 4 is what I'll be getting. Let's see. AE. If I don't write properly, then you will have errors understanding tensor product. AE, AF, BE, BF. Okay. Next, AG, AH, BG, BH, AE, AF, CE. I'm sorry, it is CE, CF, CE, CF, CG, CH. Okay. Okay. So this is the resultant tensor product of two matrices A and B. This is how I'll find out. Of course, you can find out the tensor products of X gate, Y gate. X gate is what? 0, 1, 1, 0. Y gate is what? 0 minus I 0. Okay, how do I'll just show one. You can explore the remaining ones. 0, 0 minus I 0. 1, 0 minus I 0. 1, 0 minus I 0. 0, 0 minus I 0. Okay, 0 into anything is 0 only. 1 into anything is itself. So I'll be having a null matrix of order 2 by 2 here, and also here null matrix of order 2 by 2. 0 minus I 0. 0 minus I 0. Okay. So in total, I'll be having a 4 by 4 matrix with 16 elements. This is how I'll find tensor product between vectors and matrices. Okay. Tensor product between, again, operators would be different. When I talk about operators, tensor product between operators would be different, which I will share in the next video.